Hi, welcome to the proof of the main theorem of this paper by Mantoulidis and Schoen. Here I'll just remind you of the statement of the theorem. For any g and m plus, later we'll expand this to m plus boundary to include the case of zero eigenvalue, but for now it's just m plus. We could take any m bigger than 0 that satisfies this. 16 pi m squared is greater than the area of G. In other words, this is saying that the mass is bigger than the Hawking mass because the Hawking mass is the area divided by 16 pi square root. Then there exists an asymptotically flat 3-manifold, I'll call it M or M3, with non-negative scalar curvature, i.e. the dominant energy condition, such that the boundary of M3 is isometric to S2 with the metric G and is minimal in M3. Second condition, that M3 is isometric to a mass M Schwarzschild metric outside of a compact set. And that condition 3, M3, is foliated by mean convex spheres, meaning the mean curvature of the spheres, HT, is referring to M3 basically is S2 times an interval, and so this HT, the T refers to the time of the interval. HT is less than 0 with respect to the outer unit normal of the sphere. And that these spheres eventually coincide with the standard Schwarzschild coordinate spheres. And like I mentioned earlier, the fact that we're using a Schwarzschild metric is no real physical significance other than the fact that we know its mass and it's easy to measure. And before we advance with the proof, I'd like to quickly recall a little bit about the gluing lemma, and then later a little bit about the bending lemma. But first, remember this is how the gluing lemma went. We have two functions, f1, f2. They're smooth. They satisfy these three properties. Properties are that each function, f1 and f2, are positive first derivative, positive second derivative on their respective intervals, and that this cylinder, S2 times the respective intervals, this metric is scalar positive. And condition 3 is basically a compatibility condition between these two functions. And it's saying that basically f1 is always less than f2. Remember, these are increasing. And so it satisfies to look at the boundary points. And we're saying that the derivatives match at the right endpoint of the first interval and the left endpoint of the second interval. Then the lemma stated, okay, we can glue these two things together to form one larger manifold with positive scalar curvature. And one thing to recall about the bending lemma is this auxiliary function, sigma, is given by this. And the main takeaway here is to note that sigma, if we take delta to be very small, this is, if you can't read this, this is e to the minus 1 over s minus s naught squared. So in other words, this thing goes to 0 very quickly as s goes to s naught. And so the main takeaway here is that if we take delta to be small, sigma of s is very close to the identity function. So that's going to be useful later. So now we can start the proof with this in mind. I'm going to reference this a few times, so I'll leave it nearby. We can start the proof. So given a G and M plus, construct, as we did in the collar lemma, construct scalar positive collar. And recall this collar is given by, well, it's S2 cross 0, 1. And it's got a metric that depends on this epsilon. Remember, epsilon was less than some constant epsilon naught. We're going to vary epsilon possibly to be smaller later. Recall that gamma of epsilon is given by 1 plus epsilon t squared, g of t, plus u x of t, remember this is the first eigenfunction, squared, dt squared. So recall by our construction, g of t is independent of t. It doesn't change as t goes along in the interval 1/2 to 1. And this was the whole point. We chose this auxiliary function. I think I called it alpha. We chose it to be constant on this half of this interval. And so we could say that g of t equals some rho squared times g star. And recall that g star is this round metric area 4 pi that we've been using all along. We've sort of fixed this the whole time. Another consequence of this is that this first eigenfunction, u of xt, is identically equal to constant, we'll call it t, bigger than 0, obviously. Remember, we chose these functions to be positive, for all t in 1/2, 1. So, change variables, because obviously right now, this isn't of the form that we want. Let me just bring back this here. We want it of this form. We want it of this fi squared g star plus dt squared. We don't want anything in front of the dt, and we want g star here instead of g of t. So we'll change variables. What are we going to change to? Let me consult my notes, sorry. S equals t times t. Wow, that's confusing. S equals t times t. So then this changes gamma of epsilon to be 1 plus epsilon capital T to the minus 2 s squared rho squared g star plus ds squared. So now it's of the right form. So obviously what we're going to do, take f to be a function depending on epsilon, of course, to be, well, the square root of this. So 1 plus epsilon t to the minus 2 s squared rho. And now you can calculate, I'll just write it down, the derivatives. First derivative is 1 plus epsilon t to the minus 2 s squared, the minus 1/2 times rho times epsilon times t to the minus 2 times s. And the second derivative is 1 plus epsilon t to the minus 2 s squared, the minus 3 over 2. And we get some cancellation here, actually. So we're just left with this term, e to the minus 2 rho. And now note, whenever epsilon is greater than 0, which it is, all three of these guys are positive on. Well, now this t, lowercase t, 1/2 to 1 interval becomes capital T over 2 to capital T. And so these three guys being positive satisfies condition 1. Here we're taking f1. I'm just talking about one of these functions for now, f1 to be f epsilon. Epsilon is arbitrary for now. We'll fix it later. This condition is satisfied. This condition is also satisfied because we're just making a change of variables here. And this is already scalar positive by construction. And so once we figure out what f2 is going to be, we'll make sure that condition 3 is satisfied. Of course, here, the interval a1 to b1 is t over 2t. Now, I'm going to introduce this sort of auxiliary function, capital gamma. It's going to be depending on epsilon. And I'm going to look at, this already I've shown as positive, so we're going to ignore it for now. We only care about f epsilon and f epsilon prime. So I'm going to take this to be the graph of, well, the x-coordinate is going to be f epsilon of the endpoint t, and the y-coordinate is going to be f epsilon prime of the end coordinate t. Because in this compatibility condition, it's the endpoint, the right endpoint of f1 that we care about comparing. So that's exactly what this is going to serve. This is going to serve this purpose. Now, say a couple more words about this. I've drawn a graph of this, but I'll show you in a moment. As epsilon goes to 0, well, f epsilon prime, there's an epsilon here, so it goes to 0. And f epsilon, this goes to 0, so this goes to 1, so this just goes to rho. And you can calculate what rho is. It's going to have to be equal to square root area 4 pi, or area of g over 4 pi. So here's what the graph looks like. Gamma of epsilon, which is this, the x coordinates, f epsilon t, the y coordinates, the derivative, looks sort of like this. It's asymptotically converging to what looks like y equals x. And as epsilon goes to 0, we approach this point. So I'll put this aside. We're going to be referring back to that shortly. Now we want to switch gears. We want to now look at what the other function is going to be on the other interval. So let m bigger than 0 be as stated. Recall that m is just bigger than this Hawking mass. And recall Schwarzschild metric, I spell this wrong every time. Schwarzschild metric has the form u of m s squared g star plus ds squared, and this is on the cylinder S2 cross positive wheels. And here um satisfies, I had this a few slides ago, but if you forget or you're watching this video at a later time, satisfies that of 0 equals 2m, prime of s equals 1 plus 2m over of s, square root of all that, and the second derivative is equal to m over of s squared. And now, first notice that these are all positive. So starts at being a positive number, and it only increases because the derivative is positive and the second derivative is positive. So right away, that's a good sign. That's going to satisfy condition 1, although we have to do a little bit of modification to this. Let me just get some more paper going. So notice m is chosen to be bigger than this Hawking mass, which is area g over 16 pi, sorry. Well, that implies that 2m is bigger than area g over 4 pi. So, where am I here in my notes? There. We're going to let delta of s, we're going to do similar to what we did with gamma, but we're going to do something here depending on s. We're going to let this equal, well, the x-coordinate is going to be, this is going to be the graph of, the x-coordinate is going to be and the y-coordinate is going to be u prime, m of s. So this looks like this. This is our original gamma. We note here that this point is to the right of this point because 2m is bigger than this. And as s goes to 0, delta of s converges to this point. So this point is the point of s equals 0. And so I don't really care what this looks like. I just drew it like this, but it lies in the first quadrant. That we know for sure because of s is positive and prime of s is positive. And this is the x-coordinate, and y-coordinate, so it lies somewhere up here. I just drew it like this for convenience. So for small enough S0, delta of S, when restricted to the interval 0 to S0, lies below and to the right of gamma of epsilon, this graph gamma of epsilon. So let me show you a picture of that. This is delta of S, just restricted to this subinterval, because this point corresponds to 0. This point we'll say corresponds to S0. So you just choose this so that it's cut off below this function, or the graph of this function. Now apply bending lemma. Remember that the bending lemma allowed us to get this positive scalar curvature in some annular region of the Schwarzschild metric. And so that will satisfy condition 2 for the second function. I haven't really said what the second function is yet, but it's going to be scalar positive. That's what this whole bending lemma is about, is making the scalar positive region. So let delta tilde, depending on S, equal, or it's just going to be the modified version of delta, which is um sigma of S, and sigma of S prime, just slightly modified. Note, this is why I wrote down here this little recap of what sigma was. I wanted to note that sigma really isn't changing very much. As long as we choose delta to be small, this is just basically the identity function on S. And so here, this is not really changing very much. This is not really changing very much. So for delta small, delta tilde, well, this is confusing. There's more than one more than one delta. Delta tilde of S is close to delta of S. So can make delta small enough such that this modified delta tilde restricted to S0 minus delta to S0 is still below and to the right of gamma epsilon, while staying in the first quadrant, and that's of course important. So here's our last picture that I've prepared. In fact, these two are equal here because sigma is equal to the sigma of S0 is equal to S0. So you're not changing the function here, but it's just slightly modified, and you choose delta small enough so that this guy stays relatively close to this line, and it stays within this first quadrant. In fact, I can leave this probably here. Having fixed S0 and delta, choose epsilon such that gamma of epsilon lines up, quote, with delta tilde of S0 minus delta. In other words, this is the epsilon that we want to choose. The one that makes these 2 points line up horizontally. And recall that the y-axis is the derivatives of these two things. Here we have the derivative of sigma of S. And here we have, well, I put it away already, but we have the derivative of f epsilon. And so if we take f1 equals f epsilon on the interval t over 2t, and f2 equal sigma s on s0 minus delta to s0, then this condition is satisfied. We've talked about that already. All the derivatives, or the first, second, and 0th derivative are all positive on their respective intervals. The scalar curvature of f1, i.e. f epsilon, is positive by nature, and this is how we chose sigma, so that the scalar curvature of f2 is positive on its interval. And because of the way we chose epsilon and delta and s0, condition 3 is satisfied. And so that actually concludes the proof.